Hello, my name is Minyoung Choe, and I'm from KAIST in the Republic of Korea. Today, I'm going to present our paper titled Midas, Representative Sampling for Real-World Hypergraphs. Beyond the pairwise interactions, group interactions exist in many complex systems. Such complex systems are more accurately represented as hypergraphs than as graphs. Hypergraphs consist of nodes and hyperedges, and each hyperedge is a subset of any number of nodes. Since analyzing large-scale hypergraphs is time-consuming and often practically impossible, sampling would be indispensable for various tasks. For example, if a small but representative sample of online group interactions can be used, simulation of information cascade can be run in a shorter time. Such a sub-hypergraph can also be used to mitigate the difficulty in visualizing a large hypergraph or as a way to training hypergraph neural networks. Thus, in this paper, we introduced the representative hypergraph sampling problem. Regarding this problem, we aim to answer three interesting questions. First, what is the representative sample? How can we measure the quality of a sub-hypergraph as a representative sample? To this end, we measure the difference between sampled and entire hypergraphs using 10 statistics for the structure of hypergraphs. What are the benefits and limitations of simple and intuitive approaches for representative hypergraph sampling? With respect to this question, we tried 6 intuitive sampling approaches in 11 real-world hypergraphs and then analyzed their characteristics. How can we find a representative sub-hypergraph rapidly without extensively exploring the search space? Regarding this question, we propose Midas, which overcomes the limitations of previous simple approaches and finds over the most representative samples. Our problem is formulated as follows. When a large hypergraph and a sampling portion are given, our objective is to find a sub-hypergraph that preserves the structural features of the given hypergraph under the given sampling portion. We consider 10 statistics for the structural analysis of hypergraphs. As shown below, these statistics include node level, hyperedge level, as well as graph level statistics. We numerically measure the quality of a sub-hypergraph in 10 aspects. Specifically for probability density functions, we measure the distance called Kolmogorov-Smirnov of these statistics. For scalars, we measure the relative difference. However, since the scales of the distances are different from each other, it is difficult to directly compare the qualities of sub-hypergraphs while considering 10 properties pairly. To alleviate this problem, we compute the rankings and just scores with respect to each property and average them. What we did can be explained more clearly in the given figures. The distance in size distribution is more than 10 times smaller than the difference in density. So, if we simply average them, the difference in density mainly accounts for the average of these two values. Therefore, we rank the sub-hypergraphs that we wanted to compare with respect to each statistic and compare the average value of all statistics. Throughout the paper, we used 11 datasets from 6 different domains. This table summarizes which dataset we used and what hyperedge and node represents in each dataset. We categorize 6 intuitive approaches into node selection methods and hyperedge selection methods. Node selection methods choose a subset of nodes and then return the induced sub-hypergraph. On the other hand, hyperedge selection methods choose a subset of hyperedges and return them as a sub-hypergraph. For the node selection methods, we try 4 different methods. First, we draw a node uniformly at random and we call this method RNS. As characteristics of RNS, it preserves the relative spectral properties well. However, RNS usually samples too many small hyperedges. Due to the lack of large hyperedges, the local and global connectivity is weak. Next, we try drawing a node with probabilities proportional to node degrees. This approach is referred to as RDM. We apply random walk and forest fire simulations to hypergraphs to sample nodes, and they are referred to as RW and FF respectively. We observe these 3 approaches have common characteristics. Compared to RNS, they lead to a larger portion of high-degree nodes. Resulting from the fact that high-degree nodes strengthen connectivity, the samples tend to have a stronger connectivity. But in some datasets, such as a co-authors dataset, the sub-hypergraphs sampled from these approaches have too many high-degree nodes, and as a result, they have too strong connectivity compared to the original hypergraph. For the hyperedge selection, we first try easily drawing a target number of hyperedge uniformly at random. We refer to it as RHS. This approach preserves the hyperedge level statistics nearly perfectly, in addition to connective component sizes, relative singular values, and global clustering coefficients. But since RHS is equivalent to uniform hypergraph specifications, the subgraphs from this approach suffer from weak connectivity. Next, we extend the thoroughly induced edge sampling method to hypergraphs and refer to it as TIHS. TIHS well preserves the properties that are overlooked by RHS, such as node degrees, and the connectivity tends to be stronger in sub-hypergraphs sampled by TIHS than in those sampled by RHS. In some cases, however, it leads to too strong connectivity compared to original hypergraphs. Analyzing the simple approaches motivates us to come up with our method Midas. The first finding is that RHS performs best, but its samples suffer from weak connectivity, including lack of high-degree nodes. The second finding is that degree preservation is strongly correlated with the abilities to preserve other properties and thus the overall performance. The left figure shows that Pierce correlation coefficients between degree and other properties are relatively high. The right figure shows that the average degree has a strong correlation with overlayness and density. Thus, we aim to overcome the lack of high-degree nodes of RHS while maintaining its strength. We also focus on better preserving node degrees while expecting that this also helps preserve other properties. Towards this goal, we first present our preliminary sampling method Midas-Basic. To increase the fraction of high-degree nodes, this method prioritizes hyperedges composed only of high-degree nodes. For example, when there are 2 hyperedges, E1 and E2, we aim to prioritize the hyperedge E2 because it consists mainly of nodes with a higher degree. Specifically, Midas-Basic samples a target number of hyperedges with probability proportional to the minimum degree of nodes in each hyperedge to the power of alpha. For example, let's take a look at a hyperedge which consists of nodes with given degrees. Since the minimum degree of nodes in this hyperedge is 2, in this case we draw it with probability proportional to 2 to the alpha. In Midas-Basic, we analyze how alpha affects sampled sub-hypergraphs in practice. First, we observe that the degree distributions in samples tend to be more biased towards high-degree nodes as alpha increases. This shows a promising characteristic of alpha, which can be exploited to control the bias in degree distribution. Second, we observe that larger alpha values are required to preserve the distributions as degree distributions in original hypergraphs are more skewed. Lastly, we observe that larger alpha values are required to preserve degree distributions as we sample pure hyperedges. These two observations give a direction to how we can automatically tune alpha, which leads to the full-fledged version of Midas. Let me describe Midas, the full-fledged version of our sampling method that automatically tunes alpha. Based on the strong correlations found in observation 2 and 3, the best performing alpha can be expected from the skewness of the degree distribution in the input hypergraph and the sampling portion. So, we put a linear legalizer M to the best performing alpha values on the considered datasets under 5 different sampling portions. Additionally, the alpha value obtained by the linear legalizer model M is further tuned using hill climbing. The objective of the hill climbing search is to minimize the distance between the input hypergraph and sub-hypergraph sampled by Midas-Basic with respect to the degree distribution. Through experimental evaluation, we aim to demonstrate the three advantages of Midas. Regarding quality, Midas accurately preserves the 10 structural properties of real-world hypergraphs. For robustness, it performs well regardless of the sampling portions. Finally, regarding speed, it runs fast compared to the competitors. We did experiments in 11 real-world datasets under 5 different sampling portions, and we compared it with 12 competitors, including simple, intuitive methods and 6 versions of metropolis graph sampling, which directly optimize the difference between the sampled and original hypergraphs. Midas provides overall the most representative samples in terms of both average rankings and average z-scores. Midas is followed by different versions of metropolis graph sampling, which are significantly slower than Midas. Especially, Midas best preserves node degrees, density, ovaliness, and diameter. Recall that TIHS, which Midas is based on, was not good at preserving these properties. Midas consistently performs best regardless of the sampling portions, with few exceptions. Here we compare these statistics in degree distribution, average z-scores, and average rankings. Midas is the fastest except for the simplest methods. Notably, it is 2.7 times faster than Midas-Basic with grid search, and orders of magnitude faster than most versions of metropolis graph sampling. In this paper, we propose Midas, a representative sub-hypergraph sampling method. Our contributions can be summarized as follows. First, we formulated the problem of representative sampling from hypergraphs for the first time to the best of our knowledge. Our formulation is based on 10 pervasive structural properties. Second, we observed the characteristics of 6 intuitive sampling approaches. Lastly, Guided by these characteristics, we designed the Midas, which is tested while sampling over the best sub-hypergraphs. The code and datasets used in the paper are publicly available at the given link. Thank you for listening to my presentation, and it would be a pleasure to ask me any questions about our paper. Thank you.